So the glasses, the oxide glasses, are typically understood through a model that is called continuous network model. So this is just a name of a model that describes what is the underlying structure when you look inside of that glass, right? And we will learn about what that actually means. So it already tells you it's a network model. It means that there are certain units that are interconnected, and it's a continuous, so then these units are not isolated. So just to tell you, before this particular model has been developed, many people thought that glasses are simply nanoparticles that are somehow connected to each other. But then that would not necessarily describe many of the properties that the glasses have. Okay, so let's learn about what is this continuous network model. So again, this is the state-of-the-art model that describes the structure of most of the glasses that we know today. So again, we will look at the example of SiO2. And we already know that SiO2 can exist in many forms, whether it's a crystalline or amorphous form. And the structure itself comes from the fact that, again, we are connecting silicon and the oxygen atoms. So we start from understanding how these two atoms bond. And to understand what is the type of the bonding that they form, we need to look at their electronic structure. So what I'm just writing here is the electronic structure of silicon and oxygen atoms. And when you look more closely, they will form an sp3 bond, which is also illustrated on the right-hand side of this slide. So in the center, there will be silicon atoms surrounded by the oxygen atoms. And again, there is a certain angle between these oxygen atoms that they form simply to minimize the energy, right? So what kind of bonding is this? sp3 bonding. What kind of bonding is it? I'm sorry? Covalent, that's right. It's a covalent bonding. So it's a very strong bond. So this individual structural unit in SiO2 is very strongly bonded, okay? Do you know any other type of a material that forms an sp3 bond? Very famous example of a very hard material. Yes? Diamond. Diamond, exactly. So again, this is just a specific type of bond. It's a covalent bond, and it just illustrates, so the example of a diamond illustrates the fact that this is a very strong bond, right? So silicon and oxygen atoms form a very strong bond within this particular unit. So again, if this was a crystalline material, if you were talking about quartz, then you would take this silicon that is surrounded by oxygen, and you would space them in space in a periodic fashion to get a crystalline material. So there would be the long-range order. So we would simply take these individual units, and we would put them together. And if you think about an individual unit, so you can just think that we are stacking them next to each other in the form of a crystalline material, right, when we talk about quartz. However, in glasses, you still have this short-range order, right? So you still, each silicon atom is surrounded by these oxygen atoms that are covalently bonded. So you still know what is the local environment for each atom. So there is still short-range order, but the long-range order does not exist anymore, meaning that these individual units that we just described, they still exist, so the short-range order is still there, but individual units are almost randomly distributed. But again, we will see that they're not just randomly distributed, so this is a continuous network. So there is some kind of connectivity between individual units. And this is what we call the continuous network model. Okay? So the main message again behind this is that the environment or the short-range order depends on the type of a bond that the atoms form. And then whether they are periodically arranged or randomly distributed within the space will determine whether you have a crystalline or amorphous material, respectively. Okay, so when we look at this in two-dimensional projection, so again, this would be the crystalline SiO2. It simply tells that, well, there are silicon and oxygen atoms. They're periodically arranged in space. And these individual units are almost randomly distributed in non-crystalline or amorphous SiO2. So how this particular model came about is, I already told you that people thought, well, the glasses are nanoparticles that are somehow connected with each other. But the really significant breakthrough in material science really happened in 1932 when a Norwegian-American scientist called Zakariasen noted that the glasses have very, very similar properties, mechanical properties, etc., optical properties, to their crystalline counterparts. And you know that, for example, most of the mechanical properties and electrical properties, etc., are driven by the bonding itself, right? So he proposed the model that I just described to you. He mentioned on the local scale, at the atomic scale, crystalline and amorphous glasses or amorphous materials are very, very similar. We have these units, and they're interconnected in a way that I described to you, which results in very similar properties, right? So we can think about this material in this particular way, that the bonding is similar, but there are some differences in how they are arranged in space. And if you do have these sp3 bonded silicon and oxygen atoms that are not arranged periodically in space, what that means is that there will be some oxygen atoms that are not necessarily connected with two silicon atoms, right? So, for example, if you have these units that are randomly distributed, some of the oxygen atoms will be so-called non-bridging oxygen atoms. So just to write this in a slightly larger font, so this is non-bridging oxygen. Right? So these are simply atoms that are connected to only one silicon atom. In a crystalline form, there would be another silicon atom to which this oxygen atom is bonded. But in these particular materials, this is a non-bridging oxygen atom. Yes?
So does this oxygen atom stable because the electrons are shared, or is it just -1, or is there a hydrogen connected at the other end?
So there are different possibilities. So you can mix different things within this glass, and then this will satisfy this bond. Some of them are simply non-electronically unstable in the sense that some of the electrons are simply, so their electronic structure is not satisfied anymore, right? So these are just the most stable structure would be when there would be another element that bonds and satisfies that particular bond, right? But these are just oxygen atoms that are bonded to one silicon atom, if that makes sense. But that already gives you the idea is that there are many things that you can do with these oxygen atoms, right? Because they're somehow unstable, right? So you can modify this particular material structure to satisfy these non-dangling bonds of the oxygen atoms, etc. And that in turn will modify the properties of the materials. And that's actually what we will talk about in a minute. But the main idea is that instead of having a very strong three-dimensional sp3 type of bonding, the local bonding between silicon and oxygen atoms is still sp3, but there are some of these oxygen, non-bridging oxygen atoms present in the material itself.